Okay, so good morning, everyone, and thanks a lot for the invitation. It's a real pleasure to be here. So I'm going to talk about some recent work that we are doing focused on different attention mechanisms that use these new transformations like Sparsemax and constrained Softmax. I'm going to describe what that means in a while. So basically, in a nutshell, this is what this talk is going to be about. So the Softmax transformation is, really prevalent in machine learning and specifically in language generation. For example, if you want to generate a sentence in natural language, typically you need to have a Softmax transformation that computes a distribution over words in your vocabulary, and then you sample from it. More recently, there is another place in neural networks where people use the Softmax transformation, which is to build attention mechanisms, which are also quite important in machine translation and other applications. So there's also, if you recall, Show's talk and Ruslan's talk 2 days ago. They also talked about memory networks, which is kind of related to attention mechanisms. So, for all these things, Softmax is the standard right now. So in this talk, I'm going to talk about some alternatives to Softmax for problems where you care about sparsity, or you want to put an upper bound on how much attention a word can receive. So these transformations are called Sparsemax and constrained Softmax. Both of them are differentiable, which is important if you want to run backpropagation in a neural network. So that's basically it. So Sparsemax is something that will give you a sparse probability distribution in the end, and constrained Softmax is something that allows to place a budget on attention probabilities. So we are still starting to apply this in machine translation and language generation. I think there's still a lot of things that we haven't tried yet. So if this is the application that you care most about, stay tuned, because I think that there could be some interesting ideas in this talk that can be useful. Okay, so let's start with Sparsemax. So this is a joint work with Ramon Astudillo. It was a paper at ICML 2 years ago. And just to recap, so this is what the traditional Softmax transformation does. So just to set up some notation here, so we are denoting by delta k-1 the probability simplex embedded in the Euclidean space of k dimensions. And the Softmax transformation is super simple. So we just take, so we start with a vector z, a vector in Rk. So the coordinates of this vector can be arbitrary, positive and negative numbers. We exponentiate each coordinate, and by exponentiating it, we make sure that the result is going to be strictly positive, and then we normalize it. And by normalizing, we make sure that the entire thing is going to sum to 1. So in the end, this is going to be a valid probability distribution. So it's going to be a point in the probability simplex. So one consequence of this definition is that this probability distribution is going to have full support, meaning that for every coordinate we are going to have a non-zero probability. This is because the exponential transformation is strictly positive, so we never get zeros anywhere, which is fine for many applications. But if we are working in a particular application where we would like to have a sparse probability distribution, for example, if we are dealing with a very large vocabulary and you want to assign exactly 0 probability to some words, then Softmax cannot do it. So there are some hacks that you can do. Since this is a hackathon, maybe you like the hacks, but so there are some hacks, like you can threshold the probabilities, truncating, renormalizing everything, but it just doesn't feel like the most natural way of doing it. So what we propose instead is this Sparsemax transformation, which we define in this way. So we start with the same vector z, so some vector, the same vector as before, where some coordinates can be positive, others can be negative, and we just compute the probability distribution p in the simplex that is the closest in terms of Euclidean distance to the point z. Okay, so in other words, we are computing a Euclidean projection of the point z to the probability simplex. Okay, And so one interesting aspect here is that it's quite likely that this projection is going to hit the boundary of the simplex. So if you want to get an intuition about why this is true, imagine that I have the simplex here, and there is a point z, very far away. As the point z moves further away from the probability simplex, it increases the chance that I'm going to hit a corner of the simplex, or a line connecting, 2 points, or so in general, at the boundary of the simplex. And this is something that doesn't happen in softmax. And so when this projection hits the boundary, then some of the coordinates of P, of the solution of this problem, are going to become 0. Okay, so and this is why we will get a sparse solution, and this is why we call this Sparsemax. So we are going to see that even though the way Sparsemax is defined is very different from softmax, so we have this definition in terms of like this variational definition, so to speak. So we don't define explicitly what are the operations that we are applying to Z to obtain P. We define it as the solution of an optimization problem. Even though this looks very different, there's a lot of properties of softmax that are also preserved in the Sparsemax transformation. So first of all, and I forgot to mention, but if you have any questions, something which is not clear, just feel free to interrupt me. It's better than spending the entire talk getting more and more complicated. And yeah. So
sorry.
Yeah.
Can you please explain again why it is different from just maximum?
Here?
From argmax.
From argmax. So argmax computes the discrete. The argmax typically computes what's the coordinate that has the maximum score. So it's the argmax over the vector z. Okay, but it doesn't give you. It's not a continuous optimization problem. Okay, so it's going to give you 1 in one of the coordinates and 0 on all the other coordinates. So it's going to return a delta distribution, so to speak. This is not necessarily a delta distribution. It could be, and we are going to see some conditions where this is going to become a delta distribution. But typically it's going to be sparse, but like for example, there could be one coordinate with 0.7 probability, another coordinate with 0.3, and all the others with zeros.
Which norm do you use for this formula? I mean,
okay, so this is the auto norm. So this is just the Euclidean projection. Yeah. So there's something that I'm not mentioning here. I think I will talk about that later, which is you can also recover softmax if we replace this projection by a KL projection. So if you minimize the KL divergence between P and something that uses Z. So I'm going to get into the details a little bit later. Okay, any other questions? So the first thing that we're going to do is it's not very nice to define Sparsemax in this form, because if you want to obtain some properties, it's better if you have some kind of closed form expression. So the next step that we are going to do is to take this optimization problem, write the KKT conditions and so on to try to derive a formula for P. Okay, and if you do that, then we end up with this result. So we can show by writing the KKT conditions, the optimality conditions, that the solution has this form. So the ith component of Sparsemax is going to be basically Zi minus a constant that we call tau here. And if this constant becomes, if this operation after subtracting the constant, if we get a negative number, then this is just truncated to 0. Okay. So the only challenging part for solving this problem is to actually compute the constant tau. Okay, so if you know tau, it's just applying this simple formula. So we call tau the threshold function. Okay, so you can see it as a function of z. So for every vector z, there's going to be a different threshold, and it's uniquely defined. So basically, there's a unique constant such that if you sum all these coordinates, then in the end you're going to obtain 1, which is what we want, because this needs to be a probability distribution. And so I'm skipping the actual algorithm here, but I just tell the main intuition. there is a very simple algorithm with runtime k log k, where k is the dimension of z, that basically starts by computing, by sorting all the coordinates of z, and then going through each interval between these coordinates and trying to basically check what are the coordinates that should be truncated. Because so in this formula, this entails that if you sort all the coordinates of z, some of them are going to be truncated. So the smallest values of z are the ones that are going to be mapped to 0. Okay, because we are subtracting the same constant to all coordinates zi. And the only thing that we need to figure out is what are the coordinates that are going to be truncated and what are the ones that are going to still become positive after this subtraction. And so we can do this by doing the sort and then trying out different points in the intervals of these coordinates to decide where we are truncating. And as when we figure out what is truncated, then there is a simple formula that gives us tau. Okay. So we can also speed up the algorithm by getting rid of the sort and using linear time selection. So we can actually show that this problem can be solved in linear time, which is actually the same runtime asymptotically of solving softmax, because in softmax you need to touch every coordinate of z. So both are asymptotically linear time. Of course, there's a heavier constant for Sparsemax, but it's not too bad. Actually, in our implementations we always use this simpler one based on a sort. This one, even though asymptotically is better, sometimes the constant can be pretty high. So okay, so this is if you are plugging Sparsemax in a neural network. This explains how you can do the forward pass. And we're going to see now how this transformation looks like in small dimensions. So in 2 dimensions, we can, without losing any generality, we can parameterize the vector z by setting one of the coordinates to 0, because if we add a constant to all coordinates, we get the same solution, both for softmax and for Sparsemax. And in 2D, the softmax becomes the sigmoid function. Okay, so if you just plot, the first coordinates of softmax when z is parameterized this way, so as a function of t, we get this sigmoid. Okay, this is a logistic function. This is a very well-known fact. In the case of Sparsemax, we get something that asymptotically is similar, but it's piecewise linear. So it's kind of a hard version of the sigmoid. It's going to be 0 if z is less than -1. It's going to be 1 if z is bigger than 0, and linear in the middle. So it's still continuous. It's differentiable almost everywhere except here in the -1 and 1. And the asymptotics are pretty much the same as in the case of softmax. And the same story goes in 3D. So in 3D, softmax is this smooth transformation. And Sparsemax is a piecewise linear mapping, but you can see that the asymptotics are quite similar to the ones that you have in softmax. So you can go a little bit more formal and deriving some theoretical properties of these transformations. So some of these properties are nice to have. So for example, if z is a vector of all zeros, then both for softmax and Sparsemax, we get uniform distribution in the end. So this makes sense, right? So if all coordinates have the same value, then there's no reason why we should assign more probability to some and less to others. The second property is also quite intuitive. So in softmax, if you can play with what is commonly called the temperature parameter, that can make the softmax transformation be more saturated, so be more peaked around one point. So if we start with a vector z where all coordinates of z are different, and if you make t goes to infinity, as you use this scale factor, as you increase t, then the softmax transformation is going to pick the largest coordinate of z. So it's going to give something very close to value 1 of probability to the argmax, and something very close to 0 for the other points. And the limit, it's going to be delta. So for Sparsemax, we get something very similar, except that t is finite. So we don't need to actually take the limit. There is a finite value of t, after which we get the delta distribution. And this is related to the fact that you have this saturation pattern in Sparsemax. So there's a finite value of t that makes you land in one of these regions.
So usually when you apply Sparsemax, you do the scaling, or?
That's a great question. So for some tasks that we try out, we train without the scaling, and then we apply the scaling at test time, because I'm going to talk very briefly about those tasks, but because we wanted the model to be as sparse as possible at test time. So in training, you need to be a little bit cautious, because you don't want, for example, if you have Sparsemax as an attention mechanism in a neural network, you don't want the transformation to be saturated in the earliest iterations, because otherwise you just cannot learn. So you need to make sure that you initialize to a region where the attention is not going to be too peaked, and then the model should figure it out.
Yeah, but I think in other way around. So do you need to scale to make it less sparse?
So if
it depends on initialization parameters.
Yeah. So if you
because say if you have like one output like 100, and then next value z components of c like 100, and then 10, 5, and so on.
Mm-hmm.
So it's like that. It will be your data.
Yeah, you're going to get a delta. Yeah. So this is related. Scaling is related to what's going to be the magnitude of your initialization, right? And the thing you need to be careful is that when you start training, you don't fall into a situation like that, because then you cannot recover. You don't have any signal when you backpropagate the gradients, and you don't get out of that situation. I mean, the same thing also happens in Softmax, but here it's even more sharp. So yeah, we can. If we you can use a t that is smaller than 1 to get something more dense, or bigger than 1 to be more dense. But in theory, the model should figure it out whether it should set up the weights so that it tends to give something sparse or not, depending on the final loss function that you are optimizing.
So it's like that it should optimize for sparseness by itself, not by setting because you can set a parameter which gives you the sparseness you want. Mm-hmm. Or let it to be optimized. Yeah.
Ideally, you want to learn t instead of imposing one particular value. Okay. Any other question? Okay. So these two properties are interesting. So the third one is it's also simple to prove. If you add a constant to all coordinates, then your transformation is not going to change. We also have monotonicity, so this is also quite intuitive. If you recall that to solve Sparsemax, you sort all coordinates of z. So smaller coordinates of z are going to have a smaller probability in the end. And there's also this non-expansiveness property that kind of bounds what's going to be the delta in probability between two coordinates based on how different these two coordinates are in the vector z. And there are different constants for Softmax and Sparsemax, but both can be bounded in this way. And so, okay, this is all nice, but if you want to train a neural network, you need to run backpropagation. You need to compute gradients. Which means that for this transformation, you need to be able to compute the Jacobian, which is basically the set of derivatives for every coordinate in the output with respect to every coordinate in the input. So this is going to be a matrix k by k, right? And so for the case of Softmax, there's a very compact expression for the Jacobian, which is basically this. So we take your point z. So we are computing the Jacobian at this point, z. We apply the Softmax transformation. We obtain the probability distribution p. And then we build a diagonal matrix with P in the diagonal, and we subtract P transpose, and this is going to give you the Jacobian of softmax. So for the case of Sparsemax, it turns out that you have a very similar formula. So the main difference is that now we need to define this support set. This is basically the set of coordinates that after the Sparsemax transformation gets a value larger than 0. So the ones that are not going to be truncated, we call this the support set, and we call this vector as the support vector. The name is a little bit misleading, but so it's basically an indicator vector that has ones on coordinates that are not going to be truncated and 0 on all the other coordinates. So in general, it's a sparse vector, right? Because many of the coordinates are going to be truncated. And so we can express the Jacobian of Sparsemax as a diagonal matrix with S on the diagonal minus S transpose divided by the number of coordinates that are not going to be truncated. So it's still, pretty similar to the formula that we have for softmax. Of course, if we only want to do backpropagation, you don't really need to compute the full Jacobian. We only need to compute the product of a Jacobian and a vector. So this is basically because we have some expression for the differential on the output side. So you have the derivative of the loss with respect to the variable that is in the output of softmax or Sparsemax. And we want to propagate that to get the derivative, the gradient of the loss with respect to the input. So you want to start from the output differential to the input differential. And for doing that, we only need to compute the product of a Jacobian matrix with a vector, which is more efficient than computing the full Jacobian. And so for the case of softmax, this can be computed in linear time. So it corresponds to a pointwise product between the probability distribution P and the vector that is basically our vector V, so our output differential, minus kind of the average of this vector V, where the average is computed with respect to the probability distribution P. So this is for softmax. For Sparsemax, we again have a very similar formula. So instead of P, we use this indicator vector S. Pretty much everything else is the same. But there is a very important detail here, which is we don't, so the runtime is actually better than O to the K. Because if we have computed the forward pass already, we already know what are the coordinates that are not going to be truncated, okay? And because this vector is sparse, this is basically the support of the Sparsemax transformation. Everything that is truncated is going to have a 0 derivative, okay? So we don't need to touch those coordinates, which means that the runtime for doing this is going to be sublinear. It's going to depend only on the number of non-zeros after the Sparsemax transformation, which is quite neat, okay? So to summarize, for the forward pass, Softmax and Sparsemax have asymptotically the same runtime, even though in practice Sparsemax is a little bit slower because the constant is a little bit worse. But for backpropagating, Sparsemax is faster than Softmax. Is this clear? Okay. So and basically with all these, we have all the ingredients that we need to use Sparsemax inside a neural network. So for example, we can develop a sparse attention mechanism by replacing Softmax by Sparsemax. So we tried this for this problem of natural language inference. I think that some of you might be familiar with this. So this is basically a corpus collected by the Stanford NLP group. It's basically 500,000 sentence pairs. One of the sentences is a premise, like a wedding party taking pictures, and the other sentence is an hypothesis. In this case, the hypothesis is that someone got married. And then there are 3 possible labels. So there could be an entailment, so the premise can entail the hypothesis, which is actually the correct label here. There could be a contradiction if the 2 things are contradicting each other, or it could be neutral if there is, or if you cannot conclude anything, if they are not related. So to do this, there's been several models that have been tried. We took as our baseline a model developed at DeepMind by Tim Retteshel and others, which is using an attention-based architecture. So basically what they do is there's a recurrent neural network encoding the premise, So each state corresponds to a word of the premise. There's another recurrent neural network encoding the hypothesis. Of course, they use the LSTMs for these recurrent layers. And then they use the last state of the hypothesis as a query vector to an attention mechanism, and then they want to compute attention over the words in the premise, and the output is going to be kind of a weighted representation, like a vector that represents what's the important part of the premise that is going to lead to the final prediction. So in the end, they have another feed-forward layer that looks at this state computed after the attention. It looks at the last state from the hypothesis and gives one of these three labels. So this is not the strongest system right now. So in the same paper, they have also a word-by-word attention model, which forms better. It actually computes alignment between the premise and the hypothesis, but this is not much worse than that one, and it was just simpler at the time to try out. So and so we ran several experiments. So we tried not to use any attention at all, just using the last state of the RNN from the premise. We try to use something that we call logistic attention, which is basically independent logistic activations for every word of the premise, but without trying to make the different words of the premise to compete with each other. So we don't get a normalized distribution after this. And then we tried two other things. So the first one is attention with the softmax, and the other thing is attention with the Sparsemax. And so if we look at the final scores, so we can see that both the softmax attention and the Sparsemax attention are better than not using any attention or using logistic attention. But regarding a comparison between the softmax and Sparsemax, there's not much we can conclude. So Sparsemax does better on the test set, but it does worse on the dev set. And the two perform quite similarly. But if you care about interpretability, so if you want to go to your model and look at the words that received some attention and understand why the model decided in a particular way, then Sparsemax is really neat because it can zero out all the attention that goes to irrelevant words. So we can interpret the ones that get a non-zero probability as words that are relevant for the final decision. So for example, if you take this sentence, here the premise is a boy rides on a camel in a crowded area while talking on his cell phone. And if the hypothesis is a boy is riding an animal, then the attention is only placed to the words rides, on, and camel. So all the others get zero attention. And so, this kind of makes sense because, to decide that this is an entailment relation, then camel is very crucial because the camel is an animal. So we need to pick up this relation. And also, if you have a sentence that is very long, like the last one, a man wearing a yellow striped shirt laughs while sitting next to another man who is wearing a light blue shirt and clasping his hands together. Very big and confusing sentence. There's only a few keywords are important to understand that this is a contradiction. So here the hypothesis is two mimes sit in complete silence. So if you look at laughs, seated next man and clasping, this kind of makes us able to conclude that there's a contradiction there. So this is basically what we can do by using Sparsemax in an attention mechanism. Next, we're going to see how we can use Sparsemax in the output layer. So basically, in the case of Softmax, there is a natural loss function that we can use, which is the cross entropy loss related to the logistic transformation. In the case of Sparsemax, we are going to derive something that can replace that. So just to set up notation, so we are going to consider regularized empirical risk minimization problems. So we assume that there is some loss function L, there is some inputs xi, some outputs yi. And our model consists of, let's assume that this is just a standard multinomial logistic regression model, so not a deep network, but the entire thing still generalizes to neural networks. So if this is just a logistic regression model, then we have just a matrix W and a bias vector B. We need to learn W and B to have good performance. So in the case of softmax, the natural loss function to use is the logistic loss, or negative log likelihood, which is basically computing, for a given point xi, we can compute z by taking this expression, so a linear transformation of xi, and k is the ground truth label. So the logistic loss is just minus log of the probability of level k, which is basically the kth coordinate of softmax applied to z, right? And this can also be written as minus the kth coordinate of z plus log some exp of the entire vector z. I'm guessing that you might be familiar with these expressions already. Does this sound familiar, or is this completely new? Okay. Okay, maybe familiar to some, but not for everyone. Okay, so this nothing here is new. Okay, so this is basically what you have for multinomial logistic regression, or even if you prefer to think of neural networks. If you have a neural network for multi-class classification, if you are optimizing the cross entropy loss, which is what people typically do, then your last layer is going to use this loss. Okay, so it's going to take the like scores z, where you have one score for every label, and it's going to compute the minus log probability of the true class, which is basically, it boils down to this expression. So this is nice, and of course the first thing that we thought about is, okay, let's try to do exactly the same thing for Sparsemax, trying to have like an interpretation of Sparsemax as a log probability that we can optimize. But it turns out that this just doesn't work at all with Sparsemax, and basically for the very reason that Sparsemax is interesting. Since Sparsemax is it can give you a sparse probability distribution, this means that it can give zero probability to some classes. So if for some reason it gives you zero probability to the true class, then the entire log likelihood is becoming minus infinity. So this is going to be very hard to optimize. It doesn't make much sense. So because of that, we went to a different strategy. So instead of trying to reproduce the same loss function that we have with softmax, we try to derive a new loss function such that the gradient resembles the gradients that we get with softmax. So in the case of softmax, multinomial logistic regression, or softmax as the last layer of a neural network, the gradient in that last layer is going to look like this. Okay, so the gradient of this loss with respect to z is going to be minus a delta distribution, so 1 for the true class k and 0 for all the other classes, plus the softmax transformation of z. Okay, this is a very simple expression. It's very, if you've never seen this, just try to derive this formula. It's very interesting. So by design, what we want is to design a new loss function. We call it L Sparsemax, such that this loss is differentiable, and we want the gradients of this loss to have this formula. So basically, we want the same thing that we had with softmax, but we want to have Sparsemax here instead of softmax. But the question is, we need to reverse engineer this loss. Okay, so we don't know what's the loss, right? And so, we did several attempts and so on, and in the end, we came up with this loss that satisfies exactly the property that we need. Okay, it looks a little bit mysterious at first sight. So, this is the Sparsemax loss. So it's the function such that the gradient is exactly this. And if you look at it, it's a piecewise quadratic function, and one of the components of this function is that the square of the threshold function, which is that function that I defined in one of the initial slides. Basically, the amount by which you need to subtract each coordinate of z to compute the Sparsemax. So it's very strange, like piecewise quadratic. You don't get at first sight a very good interpretation about what this is doing. But it turns out that if you look at the properties of this function, there's a lot of things here that make a lot of sense. So first of all, both for softmax and Sparsemax, this loss is going to be convex and differentiable everywhere. And the gradient is going to look exactly what we wanted, which is minus a delta distribution plus the transformation itself. So the second property is that both these losses are also invariant to adding constants. So if you add the same constant to all coordinates of z, we are going to have the same value for the loss. And third, the two losses are non-negative, so which makes sense. If you are talking about a loss function, typically you want the true class to have zero loss, and you want a bad decision to have a positive loss, but you don't want to have a negative loss. And so this is all nice, but for Sparsemax we also have an additional property that we were not expecting, but I find it very interesting, which is not only the loss is non-negative, but it's zero if and only if the score for the class K, so the true class, is larger than the score of any other class by at least 1 unit of margin. And so if you have seen support vector machines and the hinge loss, this is very similar to the margin condition in SVMs. So basically, to make sure that you have a zero loss, you need to have like a separation margin. Exactly the same thing of SVMs. But unlike the hinge loss of SVMs, this loss function is differentiable everywhere. So if you look at the hinge loss, it looks like this. So there's a point where it's not differentiable, which kind of prevents you from using smooth optimization to solve the optimization problem of SVMs. But with this loss, you can use those methods, like the fast Nesterov gradient methods and other stuff, like LBFGS. And so if you try to see how this looks like in 2 dimensions, this kind of gives some intuition. So in 2D, it happens that the Sparsemax loss reduces to something that people knew already, which is called the Huber classification loss. So the Huber loss is more used in regression. For robust regression problems, where you don't want to penalize outliers too much. But there's also a version of the Huber loss for classification, which is basically this red line here. So it's a piecewise quadratic function. It's between -1 and 1. It's quadratic. So there is some curvature here, and then after 1 and below -1, it's linearized. So this becomes a linear. So the Sparsemax in 2 dimensions, basically reduces to the Huber loss. And by comparison, if you look at the Softmax, it's the blue line here. The asymptotics again are quite similar, but they have like it's a different thing. So it seems that it never converges to either 0 and it goes a little bit slower than Sparsemax. And the hinge loss of SVMs, it's this green line, so it's non-differentiable for t equals 1. So this is kind of in between Softmax and the hinge loss. And so the next idea that we tried out is to, now that we have this loss function that can give you a probability distribution that is sparse, then you can use this loss function to generate something like a k-best list. So, for example, if you have a very large set of labels and you want to generate like a small number of labels, for example, let's imagine a document classification problem. But where you can have more than 1 label for the same document. So, for example, we are classifying news articles, but the same news article can be both about sports and politics, but it's not about economy or other topics. So you can assign more than 1 label to that document. So one way of doing that is to use this Sparsemax loss function that is going to predict some probability. Like it can say that, okay, this document is 70% about sports, 30% about politics, and 0% about anything else. So you can just take the non-zeros and state that, okay, these are the topics that the document is about. And this was the task where we had to scale up that coefficient, the scale factor that was multiplying z, so that you can get something sparser at test time. So this is basically the question that you were asking. So there's other applications like language generation that we are currently looking at. There's also some related work, related to Sparsemax. So there's this thing called structured attention networks developed by the Harvard NLP group, which is also another generalization of attention mechanisms. There's work on defining coarse-to-fine attention using Sparsemax, and there's a really nice work by Vlad Nicolai and Mathieu Blondel, recently published at NIPS, where they generalize Sparsemax to have some sort of structural structure, some kind of structure. So, for example, to try to have sparsity, but in groups of words instead of on individual words. Okay, so to conclude this first part, we have introduced this Sparsemax transformation. It's an alternative to Softmax. We derived the properties. There's a closed form expression for the Jacobian. We also proposed the loss function associated to Sparsemax. And we got some interesting results in multi-level classification. And for natural language inference, we get results that are similar to Softmax attention, but with this additional interpretability by looking at the words that get non-zero probability in the end. So, yeah, this is the end of the first part. Do you have any questions at this point before I go to the second?
Did you measure the clock watch time of training? Well, how much longer does it take to train the network, the model with this Sparsemax in reality? So
you mean like how hard is it to learn with the Sparsemax, or the computational time that it takes to do the computation?
The computational time of the whole training, how much hours does it take, how much does it long?
Yeah, so that's a good question. So for it's a little bit slower than Softmax for the problems that where we tried, but it's a very small difference. So we use the Sparsemax in attention mechanisms, and so we did some implementations in PyTorch. And PyTorch supports multi-devices, so you can have like your computation graph in the GPU, but then transfer part of the tensors to the CPU and do the computation there. And what we did there was we derived the Sparsemax nodes, by transferring everything to the CPU and using NumPy, formulas. There's a little bit overhead in doing that, and then transfer everything back to GPU. And if you compare that with just using everything on the GPU with Softmax, there's a slowdown like of, 5% or something like that. So it really doesn't dominate the computation at all. Also because we are using this for detention mechanism in machine translation, which is not where most of the bottleneck of the computation is. And regarding the ability to learn, we didn't observe any big differences between Softmax and Sparsemax. So they converge. They take the same number of epochs to converge to their best solutions.
And I didn't quite get how do we parameterize our tau?
The tau, the constant.
Yeah.
So
is it a constant? So as far as I get. Tau is a function of Z or not?
We don't need to tune it. It's automatic, right? So I give you a Z, and for that Z there is a tau that solves that problem, that makes sure that the entire thing is normalized.
Is it a hyperparameter?
No. So we don't need to tune it. It's not an hyperparameter. It's a parameter of your optimization problem. So it's like a Lagrange multiplier, if you want. So the solver figures out what's the correct value of tau that gives you the correct solution of Sparsemax. So it's not a constant that you are tuning.
And how do we parameterize it? We know tau, right?
You need to, okay, let me try to give some more details. Basically, you need to find out tau to compute the Sparsemax transformation.
Okay.
And the way this is done is we do the sort, and you try out. Okay, maybe we need to truncate the three first components, the three smallest components of Z, and then there is a formula that expresses how many components you are truncating, what's the rest of the values of Z, and this gives you tau. Yeah. Yes.
And I have a question. If your model is overfitting, then your gradients will vanish, right? So does any regularization to Z help learn the network?
So you mean having a regularizing Z with like dropout or
norm regularization?
Okay, you can do the same regularization strategies that we use with Softmax. So that there's this doesn't overfit more than Softmax empirically. It doesn't seem to be very different. Of course, we always need to regularize to make sure that you are not overfitting to your training data, but there is nothing special about Sparsemax that you don't have already in Softmax.
Well, in Softmax you still have a chance that if you're completely wrong, you'll get this some gradient.
Okay, I see what you mean. Yeah, so the only thing that you need to be careful about is in Sparsemax, you need to be careful initializing. So, for example, for some attention models, like in the Badenhaus paper, the way you compute the Z's is by applying a feed-forward layer to something that compares your source and target vector representations, and then you do like a nonlinearity, and then you do the inner product between that and a vector that is a parameter of your model. So if we want to replace that, if you want to use Sparsemax after this, then you need to make sure that this parameter of this vector that we use to compute the inner product is not going to be to have a too large a magnitude, because that could make the components of Z to have a very high variance, and this will jump right to a delta distribution in the beginning. So you need to be careful in the early iterations so that your Sparsemax is not going to saturate. And then if you have that, then the model itself is going to learn how sparse it should be. So we don't need to. Yeah. Yes.
Can you maybe comment on the paper which is called "Be careful that what you backpropagate"? Maybe you heard of it. It's your colleagues from CMU. The idea there is like throw out the softmax at all and use only linear activations with some specific loss. I think it's kind of related to what you're saying.
So is this the paper that came out from Russell's group where they have like a different parameterization for the final softmax layer?
No. It's Poland, Vanstal, Dannenberg, and Raj.
Okay, I don't know that paper.
Okay, so I'll show you and we'll discuss later.
Okay, sounds good. Okay, so if there are no more questions, then I will go to the second part. So how much time do I have left?
How much do you need?
It depends. I can skip some parts and finish faster, or I can.
Our next speaker hasn't come yet.
Okay.
So I think you can have 15 minutes.
15. Okay, that's fine.
No, maybe more.
Maybe more.
25.
Okay. Well, if I'm taking too long, just stop me. Okay, so the second part, so this is work that we recently presented at TMNLP. This is the paper, Fully Differentiable Neural Lucifer Staggers. And it's introducing another transformation that we call constrained softmax. And so this is what constrained softmax is doing. So it resembles softmax once again, but it allows imposing hard constraints on the maximal probability assigned to each word. So for example, if for some reason you know that this word should not receive more than 0.5 probability after detention, this allows you to set this upper bound. And the way we define it, it's super simple. So it's basically the probability distribution P that minimizes the KL divergence between P and the softmax transformation, subject to these constraints. That this is the vector of upper bounds, the U vector. So the constraint is that P cannot exceed these upper bounds. So it's basically this distribution closes in terms of the KL divergence to the softmax, but satisfying these constraints. And so this is, there's this framework of posterior regularization, which is kind of related to the way we are defining this transformation. And there are some particular cases. So for example, if all the upper bounds are larger than 1, these constraints are not going to be active, because every probability distribution, every coordinate already needs to be less than or equal to 1. So if our upper bounds are too loose, then these constraints are never going to be active, and you just recover softmax. So the KL divergence becomes 0, and you just get the standard softmax transformation. On the other hand, if our vector of upper bounds is in the simplex, then all these constraints are tight, because there's only one p that can satisfy these constraints, which is p equals u. So these are the two extremes of this transformation. And so, okay, how can we evaluate this transformation? So there's an algorithm that we have derived that takes, again, L log L time. It also requires computing a sort operation, and we do this by computing the coordinates that are met strictly. We write the KKT conditions. I'm going to skip details because there's not so much time. But it's the same idea that we had with Sparsemax. So we need to sort. In this case, we are not sorting Z. We are sorting something that also uses the upper bounds. And after this sort, we can figure out what are the constraints that are going to be active, and what are the constraints for which you can just do something similar to a softmax. So this explains how we can do the forward pass, and now to backpropagate. We can again backpropagate, so we can backpropagate in linear time. So it's the same cost as the standard softmax. So by the way, we can so we are going to compute gradients not only with respect to Z, but also with respect to the upper bounds. And this is neat because we can, so the upper bounds U can also be a function computed in your computation graph. So there could be a function of the inputs of your neural network. And this is actually something that we're going to use in our application. And so in the end, you want to backpropagate not only with respect to Z's, but also with respect to these upper bounds. And it's very simple to backpropagate, as we have computed the forward pass. So these are the expressions. Everything can be done in linear time. I'm going to skip details. If you are interested, you can take a look at the paper to see proofs of these things. And so this transformation opens the door for using this constrained softmax attention in a neural network, backpropagating both through the scores and through the upper bounds. And we are going to show how it can be used to derive something that we call neural easy first decoders, which is the main topic of the MNLP paper. And so this is the motivation for these easy first decodings. So if you think about it, the current generators, things that you see in language models and neural machine translation models, they always decode greedily from left to right. You can do things like beam search, but it's essentially still pretty greedy. Of course, people do that because it's computationally convenient. You can also argue that humans process language in a similar way, so in spoken language at least. But on the other hand, this introduces error propagation and label bias. So if we, for example, in machine translation, if you are generating the target sentence, the translation, if you make a mistake in the beginning, then it's going to be quite hard to recover from that mistake. This is what is called error propagation. So in this work, we are going to do something different, which is instead of doing everything left to right, we are trying to let the model learn what's the optimal order by which it should decode. So in fact, I'm not going to show sequence-to-sequence problems, but just sequence tagging, which is kind of a first step. So in sequence tagging, you are given a sequence, for example, words of a sentence, and we want to compute a tag for every word. So for example, part-of-speech tagging, named entity recognition using BIO tags. You just want to compute a label for every word, but the output sequence is the same size as the input sequence. So we're going to see that this makes it simpler to drive an algorithm for this. And so the main key aspects of our proposal is that this idea of easy first taggers have been tried by other people long time ago, before neural networks got so popular, but the entire thing is not fully differentiable. So if you want to try to use the same ideas using neural networks, you need to go to something like sampling, reinforcement learning, and so on. And here we are trying to avoid those things. I don't have anything against reinforcement learning, but it can be a little bit painful to make it work. So what we offer as an alternative here is something that we can that is fully differentiable, so you can backpropagate all these decisions. And they're going to look at 3 tasks: part-of-speech tagging, named entity recognition, and word-level quality estimation. So before going into our algorithm, let me just give a sketch about what the easy first tagger does. So the key idea is that we try to perform easier decisions before committing to hardest ones. So for example, if you're doing part-of-speech tagging, maybe you can find words that are not ambiguous, or for which you are very confident about what the part-of-speech tag should be. You just tag those, and then you condition subsequent decisions on decisions that you have already made. So in algorithmic form, you keep track of the set of positions for the words that you have tagged already. So this set B is initialized to empty sets, and you keep track of kind of a sketch set of our output, which is basically the labels, the tags that we have computed for words in those positions. And at each time, you go through all positions that are not covered yet. We compute a score for every possible tag at that position, and then we just pick jointly the position and the tag for that position that maximizes the score. Okay, so it's like in part-of-speech tagging, you have several possible tags for every word. You go through all positions, you compute the scores for all tags, and then you just pick the position and the tag that maximizes the score. It's kind of an heuristic, but it works well for some problems. And so then you add to your sketch set the pair position and tag, and we add to the set of covered positions the position that you now covered. So it's a very simple algorithm. So of course, if you want to train it, there's a challenge here, which is there's a factorial number of orderings that can lead to correct predictions. So you don't have the ground truth about what are the best positions to tackle next. So you need to either marginalize out this information or do something smart. So the usual approach is, they use perception or gradient descent, but they don't backpropagate through the ordering choice. So they use that algorithm and then only backpropagate to tag mistakes. So for example, if you're using perception, you are following that recipe in the previous algorithm that I just showed. You tag the complete sequence, and then if you made a mistake, then the perception is going to try to correct the model. But there's nothing that tries to correct for a wrong choice of order. So this is we can argue that this is a bit suboptimal. So again, it's sucky, so it's good for a hackathon, but maybe not if you want to develop something more principled. So you can use reinforcement learning for this if you use, for example, policy gradients. So you can do complete rounds of predictions, picking order and a tag for that words, and having a reward function in the end, and then trying to backpropagate that reward through all the actions that you have taken. But here we are trying to propose something different, where you work with a continuous space of actions. So, and the fact that it's continuous is going to be important because you can backpropagate the entire thing. So this is the key ideas. So instead of picking the easiest position at each point, we are going instead to compute an attention probability over the word positions. So you are not really picking a single word, but you are computing a distribution over the words. The second thing is that we are not going to have a set of positions that have been covered. Instead, we're going to maintain a cumulative attention vector. So this is basically how much attention have we already placed to each word. Okay, so the intuition here is that if a word has received already a lot of attention, it's essentially covered. So we don't need to waste more attention for that word. You should look at the other words instead. And finally, instead of a sketch set, which contains the position and the tag, we are going to have like a sketch matrix that contains some sort of output embedding for each position. So it's kind of like a sketch of what we're going to produce in the end. And this is kind of a diagram, describing how our model looks like. So basically, we are. So the task here is part-of-speech tagging. We start with a sentence. This is the input sentence, 6 words. We use BiLSTM to compute states for all these words, and then we have this loop where we are performing several steps. At each step, we are going to compute something that uses the current sketch that we have for the output, which is initialized to a matrix of zeros. So there's no information when we start. And based on this sketch, we are going to use an attention mechanism to decide which words we should be looking at next. Okay, so this is going to define a probability distribution over the words. So this bars here denotes the probability that we are assigning to each word. So for example, here in the first step, we decide to put most of the attention to the third word, AP. Then for the second step, we put most of the attention to the fourth word, then to the fifth word, then the sixth one, and then the second one and the first one. Okay, so the idea is that we need to have some sort of diversity for these attentions on the different steps. And then, given the attention, we update our sketches. So basically, if we know, okay, now I'm looking at this word, so now I need to update, the column corresponding to that word. So we are going to do these updates continuously using all the attentions, also not just for the word that receives the most attention, but this is kind of refining our sketch view of our outputs are going to look like. And then after we are done, after we perform all these steps, then we are going to go through a softmax, and this is going to produce the final sequence of part-of-speech tags. So this is the main idea. So okay, before I think I actually will skip this. But do you have any question about this general framework?
How do you use this kind of softmax here?
Okay, so that I'm going to explain a little bit later. Yeah. And yeah.
So for every word you have, what is included in this sketch matrix?
You can regard each column of this matrix as an output embedding for the word. So for example, for the word AP, this will be like a embedding size vector that is going to kind of be very aligned to the part-of-speech tag proper now. So this should be these sketches should be very discriminative for the labels that we are going to assign in the end. Okay, so I'm going to skip this first part because we might not have a lot of time. I'm going to jump to the interesting part, which is basically where we use constraint softmax. Okay, actually I think I still need this. So okay, so let's denote the columns of the sketch matrix by small s. Sj is the jth column. N is denoting here the sketch step, so at each iteration of this algorithm. And what you're going to do is for each word in the sentence, we compute a state Ci that kind of summarizes the surrounding local information about other words and sketches. So for example, if you are with a word, we are looking at the neighboring words, but also the neighboring sketches that we might have already produced for those words. Because they are going to influence the decision that you're going to make for this word. And this is done by just concatenating all the states that come out of the BiLSTM. So this is input information, and also concatenating all the sketches that we have for the neighboring words, which is kind of the output information. And the main intuition is that current sketches carry information about the neighboring words predictions, and we can use that for predicting with the next word. And now the next step is, okay, now that we have these vectors Ci, we are going to compute an affine transformation of Ci, and using something similar to Badanao attention. So this is basically feed-forward layer, and then an inner product with a parameter vector v. And this is going to give us a score for every word. So we are going to have a score Zi for every word of the sentence. And then you need to convert that to an attention probability. And this is where we are going to use the constraint softmax attention. So basically, we keep track of how much cumulative attention have been placed to each word. This is the beta vector. Okay, so at this time, beta is storing, okay, this word already received 0.8 attention, this word already received 0.2, this one only received 0.1. And what we are going to do is, we are going to set as upper bound 1 minus that number. Okay, so if a word has already received 0.8 attention, then it only remains 0.2. Okay, so this means that each word gets 1 unit of credit, 1 unit of budget for the attention, and then it needs to use it, in a smart way. And this makes sure that we have this, what we call the evenness property. So each word gets the same unit of attention that all the other words, and this attention is going to be consumed while the algorithm is being executed. When the credit expires, then this word receives exactly 0 attention. There's no more attention for this word. So this kind of mimics the behavior of the vanilla easy first algorithm, where we don't touch words that have been, or bound positions that have already been covered. And so, okay, given this attention, then you need to update the sketches. And to do that, what we do is to, take again an affine transformation of the, our inputs, and multiplying that, doing a pointwise multiplication by the attention for every word. So this means that words that have 0 attention are going to have zeros here, so they are not going to be, the sketch for those words is not going to be updated, right? So for example, if a word has exhausted their attention, then the sketch for that word, the vector Si, remains the same, because we are going to have a 0 here. Words that receive a lot of attention, they are going to be more updated, okay, because they get everything that comes out of this tonnage transformation. So if in the extreme case where the attention is completely picked on a single word, so for example, if the word at position K gets all the attention, then the sketch update is only going to affect that word. So you get something that looks like this, okay? So it's going to get the score, and it's for the other words you get exactly the same sketch vector that we had in the previous step. So to wrap up, we were going to do this n times. The standard choice is to do it as many times as the number of words in the sentence. But we can also do more steps or fewer steps. In the end, we're going to obtain the final sketch matrix with all the columns updated, and then we just generate, we just use a softmax to compute the probability for every tag conditioned on this sketch. So let's see some experiments. So the first set of experiments is for part-of-speech tagging. We use the universal dependencies dataset. We picked 12 languages, trying to have a good mix of different language families. The encoder is a BioSTM, so you choose the number of steps as the same as the number of words. And as baselines, we compared with a feature-based linear model. It's a little bit outdated now, but it still gives very strong scores for part-of-speech tagging. We also use the BioSTM tagger and just the vanilla easy first tagger. And so, there's a lot of numbers here, but if you look at the final averages, then we can see that, the neural, so okay, so these are different configurations for the neural easy first. The one I talked about is basically the last row, okay, so we can ignore the others. So we got slightly higher scores by using constraint softmax than by using, for example, BioSTM tagger or the vanilla easy first tagger, but the difference was not huge. So this is not a huge win. Apparently, we got better results for almost all languages we tried, but the final difference is pretty small. And of course, we are all these models are doing better than the linear tagger. So yeah, the other configurations we are comparing against is by using different attentions, softmax and sparse-max. So apparently, the constraint softmax is a much better choice than, for example, sparse-max, and softmax is also worse. And yeah, so that's basically it. But so this is the thing I find more interesting. So if you look at where the attention is going, so this is showing for each step of this method, where okay, so it's going from the top to down. So on the left we have the constraint softmax method, which kind of starts by putting most of the attention to the word thought, and then it looks at have and so on, and the last piece of attention is going to the word I, which is not exactly what you were expecting. So this is actually putting more. It's not doing. It's not having an easy first behavior. It's actually putting most effort on trying to figure out the part of speech tags, for example, of verbs. And my intuition is that by doing that, it's trying to figure out what the entire argument structure of the verb is going to look like. So this is going to give a global perspective of what the sentence is going to look like. For example, if you look at the vanilla easy first algorithm, it's really doing easy first. So it's starting by punctuation, then the words, then book, then I. Actually, book is also ambiguous, but anyway. So you're getting like different behavior than we get with vanilla easy first. And the other two maps are showing what we get with constraint softmax, where we are putting the same attention over and over to the same words, so you don't have this diversity in the attention. And in the case of Sparsemax, there's words that never receive any attention. So there's a So Sparsemax performed very badly on this task. And so if you look at the plots for constraint softmax, they have this kind of raindrop appearance where suddenly all the attention is exhausted and it's zero afterwards, which is basically when we expire all the attention that each word can get. So okay, we also tried to apply this to named entity recognition. So we use data sets from Cornell shared tasks. We did two experiments. One where we use a standard softmax output layer, and the other one where we use a CRF layer in the output, which is closer to the state of the art. And there is one crucial difference between the named entity recognition and part-of-speech tagging, which is in NER, most words are not going to be entities. So there's a label that clearly dominates all the others, which is the outside label. And our intuition here is that, okay, since there is kind of a default tag to these words, maybe you don't need all these sketch steps. Maybe you can have fewer sketch steps than the number of words of the sentence, because this has an impact in runtime as well. So if you have fewer steps, then it's going to be faster. And so these are the numbers that we got, both for BileSTM output layer and BileSTM CRF. So in this case, okay, I guess you can, I didn't talk about the approach in the first line. So the other trees are showing what we get with 5 sketch steps, with 10 sketch steps, and with as many sketch steps as the number of words in the sentence. And we can see that for many cases you can actually go away with 5 steps and it still works. Sometimes it gives you the best performance. And all these models outperform BileSTM CRF tagger. So it seems that we are really gaining by using this easy first approach here. If you look at the attention maps, then we can see, on the top we have like just using 5 sketch steps, and here as many sketch steps as the dimension of the sentence. We can see that by using 5 sketch steps, the model learns to kind of do some sort of parallel reasoning. So for example, for the words US Open Tennis Championship and National Tennis Center, it's kind of doing in parallel, assigning labels to these two entities, and it's completely ignoring words that do not belong to any entity. So it doesn't put any attention on those words. While the method that is forced to go through all the words, it doesn't exhibit this parallel behavior that much. So it goes really word by word. So we also we are currently trying this out for machine translation as a way of modeling fertility. So this is like a typical mistake in neural MT systems. So here we are translating from Romanian to English, and you have these repetitions. So this, if you have played with neural MT, you might have seen this kind of stuff before. So this is repeating a 50-year-old man, twice. And so one thing that you can do is to put an upper bound of attention to prevent these repetitions to happen. So if we prevent these words to receive too much attention, then you can avoid this thing to being repeated over and over. And actually, by doing that, we managed to solve the problem with this sentence. So this is something that we are still trying. It will hopefully be a submission at ACL. But the idea is that we can use this to model word fertility. And this is it. So, in this talk, I talked about these two new attention mechanisms, one using Sparsemax, the other one constrained Softmax. They are both end-to-end differentiable. So if we want a sparse probability distribution, then Sparsemax could be a good choice. If you want to impose a budget of attention, then constrained Softmax could be the best choice. We can use constrained Softmax for fully differentiable easy first search. We can also use it to model fertility in machine translation. This is what we are doing right now. So as future work, so constrained Sparsemax is kind of a combination of these two. We need this already, so this is also something we are trying out. But we can also have like something which is sparse, so where every attention step is sparse, and we also have kind of a budget of attention that each word can get. So we have sparsity in these two directions. It's also interesting to try to put structure and sparsity together. We are also working on that. And finally, to use this idea of posterior regularization as a way of extending constrained Softmax even further. So this is basically it. This is the hiring slide. So we are, if you are excited about MT crowdsourcing, and if you like to live in a warm place, then we are hiring at Babel. So we are doing very well. We are mixing machine translation with human post editors, and there's a bunch of interesting machine learning problems there that we are solving. And we just got Series B funding, so we are going to expand the team quite a bit this year, and we are hiring for research scientist positions. So yeah.
So what about surfing skills?
Yeah, I forgot about that. So we have so one of the big things at Babel is that everyone is very excited about surf. Not me, but most of the others are. And we offer surf lessons as well to people who join the company. So yeah, there's the opportunity of going surfing once in a while and learning how to surf. So if you don't know to surf, you will have the chance of learning it.
Okay, let's thank the speaker first. And now we have time for 1 or 2 questions if you have any you haven't asked yet.
Can you tell about the problems you said in the end between on machine learning and crowdsourcing?
So the kind of problems that we are trying to address at Babel. So one I didn't talk much about that here, and it's also actually part of the Easy First paper. But one of the topics that we are very interested in is quality estimation. So this is basically when you have like something that was produced by a machine translation system, and you have your original sentence. You put the two things side by side and try to estimate what part of the translation is correct and what part we are not very confident about. And this is very important if you have a human post-editing the sentence, because you can make the human's job much more efficient. So for example, if you are translating a long document, maybe most of the translation is fine, but there's like 2 or 3 points that we are not very sure about. We can just have like highlight those words that we are not very confident and direct the human to go fix those words. And by doing that, he can be much faster than if he has to look at the entire document. We can also, and this is quite relevant if you use NeuralMT. So most of NeuralMT is much more fluent than previous phrase-based methods. So you get a very fluent output, which is good, but it can also be a little bit misleading, because if the human translator only looks at the target sentence but doesn't check the source, then there's a chance he thinks that the translation is fine, but it can be completely wrong, right? So one thing that we are doing very actively right now is also to realize when there is something missing coming from the source or some mistranslation of the source, and also highlight source words so that they can look at the source when it's necessary. So there we have like a mix of these problems. So there's problems in which you can use machine learning to help humans be more efficient. And we also have the others, which is, as we get more data, then the humans fix the output of machine translation. This is kind of a data generating machine. So we can, you obtain a larger in-domain corpus that you can use to retrain your machine translation systems. So we have humans helping machines and machines helping humans.
Okay, thank you. One last question, maybe. Okay, so let's thank our speaker.